Not our last regularly scheduled lecture. Now, that doesn't mean that we're not having class the rest of the week, but it does mean that if you want to come and ask questions to study for the test on Thursday, then, come during our regular class time on Wednesday and ask lots of questions. If you want to start studying for our final, we'll be doing that basically all of our regular class periods left, which arguably is only Friday after the exam. But, if you want to ask questions after class or whenever on either the final or any part of the test that's on chapter 9 and 10, feel free. We only have one last topic to talk about, and that's the idea of non-ideal gases. So far we've always been saying that we're using the ideal gas law, and we even had that kinetic molecular theory of gases that gives us a nice molecular viewpoint of where that non-ideal gas law came from. And what we want to do is we want to look at sort of violations of that, or what a real gas, or how a real gas behaves. And what we'll find is that for most calculations that we're doing in this class, you can use the non-ideal gas or the ideal gas law at low temp or at regular temperatures and pressures, but that if we go too high in pressure or too low in temperature, there's some correction factors that we start having to use, and we want to use a non-ideal gas law, or if it's something truly important, there's even more complicated equations beyond that. So our two assumptions that we had made that are somewhat false are that the volume of the particles is much, much less than the volume of the container. And so that was sort of saying that since it's mostly empty space, the atoms don't get a chance to interact very well at all, and we don't have that. And that's a fairly true statement. At 1 atmosphere and 0 degrees Celsius, it's approximately 0.05% of the container. So that's a pretty small amount of error. But if we go up to, say, 500 atmospheres and 0 degrees Celsius, then that's about 20% of the container. And so, when our assumption starts being off by 20% or more, then we know that we're going to have problems. Our second thing that we have to worry about is molecular interactions. So we said that gas molecules do not interact. And again, that's a good assumption at standard temperatures and pressures, meaning the molecules really are far apart and they really don't tend to interact. And so what we find, though, is that at about 300 atmospheres, those intermolecular forces, or those attractive forces, start to matter. And what that does is that here the volume, both of these tend to make the volume of the container appear either larger or the volume of the container to appear even smaller. And so the correction factors, or the actual things that are wrong with the non-ideal gas law, tend to even cancel out at sort of intermediate pressures. And it's not until the terms get fairly large or the temperatures get really, really small and those intermolecular forces kick in more that we see really big deviations from non-ideal gases. So the person that sort of went through this all is named van der Waals. And you might remember him from chapter 10 in that a lot of our intermolecular forces are lumped together and we can call them van der Waals forces. And what he did is he came up with two correction factors. He came up for a correction factor for the pressure and a correction factor for the volume based on those two parts that we did. So the first one we'll take a look at, and I think this is the opposite order we covered them in, is that intermolecular forces are important. Especially at high pressure or high density. Meaning, if we've got a lot of molecules in a very small space, they're going to interact a lot more frequently. And the assumption that he made is that it occurs only when two molecules interact, And so he didn't even take into account like three-body collisions. And so you can go do whatever you want. I'm just talking, it's recording. You can take a nap, I don't care. The probabilities of the two molecules being in the same place at the same time. So what he said is that the real pressure of the pressure of an ideal gas is equal to the pressure of the real gas plus a correction factor that depends on the intermolecular forces and is gas specific, so specific for each element. And then we have to multiply that correction factor by our density, which is really just the number of atoms over the volume. And then we have to square that term to represent the probability of a collision. So this represents the probability of a collision between two molecules or atoms. And if we take a look at this correction factor, what this says is that the pressure of a real gas is less than the pressure of the ideal gas, meaning that we have an increase or a decrease in pressure from what we'd expect. The second correction factor is for the volume, and that one's a little bit more easier to understand, I think. The idea is that the volume of an ideal gas is equal to the volume of a real gas minus an NB term, where B is again a molecule specific correction factor, and it essentially represents the size of an atom. And so those correction factors can actually be used to kind of look at what we would consider the diameter or the radius of an atom and give us an estimated size. And of course, n is simply the number of moles. And so the idea is that the ideal volume that we should use in that equation is the real volume of the gases minus, or the real volume of the container minus the amount of space that the gases are taking up, and that's just the number of moles of gas times the space that the atoms take up. So we can, of course, combine those into two, and we can say that our pressure correction term looks like this. And so this is mimicking PV equals nRT. And our new volume correction factor is V minus NB, equals nRT. And it turns out that most often what we're solving for is pressure in these cases. And so most often we just convert it into the pressure form of the formula. So if I rearrange that equation and solve for pressure, I get that it's nRT all over V minus NB minus N squared A all over V squared. And so that's the van der Waals ideal gas law corrections. And we can get an idea of the magnitude of these corrections by doing a couple simple problems. So first we'll take a look at it at normal sort of room temperature. So if I say that I have a volume equal to 22.4 liters, that means that I also have the number of moles is equal to 1 mole. And if I say my temperature is 0 degrees Celsius, or 273.15 Kelvin, and we'll use oxygen as an example. So the correction factor A for oxygen, not A2, but O2, is 1.36 liters squared atmospheres all over moles squared. And I forgot to point out that you should notice that these correction factors have units that cancel out to give the units that we'd expect when we add things together. So you don't have to memorize any of these correction factors. They would be given to you on a homework. They'd be given to you on a test. I'll probably just put a bunch of them on a cheat sheet at some point for people to use but I haven't quite gotten to that point. The correction factor for the volume is 0.0318 liters per mole. And so what that's saying is that if we would expect normally the liter of a mole of gas to be 22.4 liters, that a mole of O2 gas really takes up 0.03 of that, which again is about 0.05% at room temperature. And so, we don't worry about that too much. So if we go ahead and take a look at our correction factors, if we take a look at that first part of the correction factor, just the nRT all over V minus NB, we get that it's 1.0014 atmospheres. So what this is saying is that we have an increase in volume due to the space the atoms take up. And then if we take a look at our other correction factor, the minus n squared A all over V squared, we get that it's minus 0.0027 atmospheres. And because this is a negative number, what this is saying is that we have a decrease in volume due to the intermolecular forces. Now notice, those are both very small changes, and in fact they're opposite in magnitude, and so when I combine them together to get the real pressure, I get that pressure is equal to 0.9987 atmospheres. And remember that our pressure, if we just use the ideal gas law, says it should be 1 atmosphere. And so we notice that the deviation at room temperature or at low pressures like 1 atmosphere that we're used to doing is pretty small. I would say that 1 and 0.9987 are pretty much the same. I would argue that if you got 100% on a test and you got 99.87% on a test, you'd probably be happy in both cases because the values are, so close together. Now, if we do these calculations for higher temperatures, and again, I'm not putting in all the values or showing things, but if we take a look at what would happen if we say the pressure is equal to, we're solving for pressure. Our volume is equal to 0.200 liters, and according to we have 1 mole, and then in this example we use CO2 at 0 degrees Celsius. And I didn't write down the correction factors because of course that would be silly. Let me write them down real quick. So for CO2, A is 3.592 liters squared atmospheres mole squared. B is equal to 0.04267 liters per mole. And if I do a bunch of calculations, what we find is that the pressure according to the ideal gas law, that's just PV equals nRT, is equal to 112 atmospheres. But if we do the van der Waals corrections, then we get that P plus 3.592 liters squared atmospheres moles times 1.00 moles, and that's got to be squared all over 0.200. Let me put the liters in. Squared. There's our pressure correction term. And then our volume correction term is 0.200 liters minus 1 mole times 0.04267 liters per mole. And that's supposed to be equal to nRT, so that should be equal to 1 mole times 0.0826 liter atmosphere mole Kelvin times our temperature, 273 Kelvin. If we arrange that and solve for P for the van der Waals equation, what we end up with is a pressure of 52.6 atmospheres. So the ideal gas law predicts a pressure of 112 atmospheres, whereas van der Waals says it really is only 52.6 atmospheres. That is a significant difference, meaning that we probably should use the van der Waals equation for most circumstances. Another way to look at these deviations from ideal behavior, I've got another PowerPoint slide here, there it is, with a couple graphs in it. One way to look at deviations from standard behavior is to simply solve for, oops, let me turn the pen on, the ratio of PV over RT to the pressure at different atmospheric pressures. Meaning, what we're really looking at is that if the ideal gas law were perfect, we just have a dotted line at 1, and PV over RT would always be 1, because at 1 atmosphere we would have, 1 for the ratios. But you can see that for a bunch of different gases, there's significant deviations that early on for most of the gases, PV equals nRT actually overestimates what we should have, but that at much higher pressures, that term that controls that's due to the intermolecular forces, means that we really should experience much higher values than we do normally. And you can see that it depends differently for different gases. Gases that have larger intermolecular forces are going to have or show more of a deviation. Gases with weaker intermolecular forces are going to show less of a deviation. And then we've got another picture here, and what this is doing is it's looking at what the effects of different temperatures are. And notice that, at 200 K, there's still significant deviations. At higher temperatures, the deviations are actually less. And if we went to lower temperatures, we'd start to notice that the deviations are even more. So that line might be 100 K. And the reason we know that those deviations have to occur is that at some point, the intermolecular forces are really strong enough to condense from a gas down to the liquid state. So we know at some point PV equals nRT, and even that van der Waals corrections for it has to totally break down. So that's some information, I guess, or kind of a theory or an idea about how to look at things from sort of a chemistry perspective. And what we should take from that is that our general procedure for doing things is that we always start off with our easy theory. That's PV equals nRT. And I got to be honest, many of those early theories, for instance, PV equals nRT came up with in the 1800s, meaning that because gases obeyed physical laws, it was very easy to do measurements on them. It wasn't until even later than that that we started to have those van der Waals. And that was sort of the early 1900s. And what we see there is, and I keep spelling with 2 L's instead of 2 A's. It's bugging me. I knew it looked funny. For the van der Waals corrections, we have to have a little bit more knowledge about the atoms. We have to have an estimate of their size, or at least make enough measurements that we can make a correction factor for that. We also have to have a correction factor for their stickiness, meaning the intermolecular forces that are actually occurring between those molecules that make them want to be attracted to each other and that decrease the pressure in the containers. And then, of course, after this, we have more and more complicated theories. It's kind of like what we saw in chapter 6 and 5, and I forget which one it's in. I think it's mostly 5, actually, where we went from, simple Rutherford model to the Bohr model to the de Broglie model to eventually Schrodinger's model for an atom. And it's the same thing that happened when we went from Lewis structures to valence bond theory to molecular orbital theory. We start off with an easy theory that explains most of it, that gets us probably like 90% of the picture. And then we like to go and show 1 or 2 more theories beyond that so we can start to see where things break down. And we can also start to see why science gets extremely hard, because those theories get more and more mathematical. I think in order to be a chemist, and actually to be any sort of good scientist, a lot of times you need to have just a very strong math background, since math is what we end up describing most things with. So, short lecture today because we just had that little bit of chapter 9. A certain part of me says I should just dive into chapter 11, but